mechanism is called a parallel prefix sum method. Okay, and let us see that what kind of complexity we get by this method. Okay. So, for this method we will first define a few things. Okay. So, let this dot from D cross D to D be an associative operator. Okay. So, this is just a function from a, so D is some domain and this is just a function from D cross D to D. Okay. So, it takes a tuple and it outputs a element of D, and it is an associative operator. That is the only assumption that we are making on this function. Okay. So, associative means that x dot y bracket dot z is the same as x dot y bracket z. Okay. So, now what we would like to compute is let, okay, so given x0, x1 up to xn minus 1 elements of D, okay, we want to design a circuit to compute x0, then x0 dot x1, then x0 dot x1 dot x2 and so on till x0 dot x1 dot so on till x of n minus 1. So, we want to compute these n minus 1 quantities. Okay. So, if you think of it as a circuit, so what I want to do is I want to build a circuit that takes x0, x1 up to x n minus 1 as input, and it must output x0 here, here it must output x0 dot x1 and so on till x0 dot x1 up to x of n minus 1. Okay. And let us give a name to this circuit. So, we will do this in a recursive manner. So, let us call this with n inputs, let us call this as Pn, the circuit which does this. Okay. So, so this is just an abstract problem, we are not directly looking at addition right now, but for an associative function over some domain, we want to see if we can build a circuit which computes this for us. Okay. This is our problem. So, how can we achieve this? So, to achieve this, so first of all let us look at a base case. Let us say when we have n equal to 2. Okay. So, for n equal to 2 we can just have a simple circuit. We can have a circuit which essentially, so this is my circuit P2, it takes x0 and x1 as input and x0 directly becomes 1 output, and here I have let us say inside this I have a circuit for this dot operator which will take both these two as input and it produces this as output. So, x0 dot x1. Okay. So, this is for P2. Okay. And you can see that this is a circuit of size 1. So, this has let us say, by 1 what I mean is that there is one gate for the dot operator. Let us assume that we are counting the number of dot operators in the circuit. So, this has one dot operator and the depth is again just 1. Okay. So, size and depth for P2 is equal to 1. So, this is the base case for us. Now, we define something. Okay. So, we will define a function, let us call it as f of I, which is equal to C, P or G. Okay. So, these are now, so now we kind of try to relate this operator to our original problem, to the addition problem. Okay. So, we want to kind of we want to define it in terms of the addition problem, and here we will take our domain also to be C, P and G. Okay. So, when is Fi equal to C? So, Fi will be equal to C if, so this is the clear bit. So, if Xi or Yi equal to 0, it will be equal to P if Xi parity Yi equal to 1, and it will be equal to G if Xi and Yi equals 1. Okay. The same definition for this, but this is what we have. And now what we know is that from the earlier observation, what we know is that some Ci plus 1 is equal to 1, okay, if there is well, the bit gets okay. So, before doing this, let me just define the operator. Actually, what is the definition of the operator over here? So, the dot operator is now defined as follows. So, we will have a 3 cross 3 table. We have C, P, G. Here also we have C, P and G. So, essentially our domain is D. Okay. So, for every tuple in the domain I have to define what the dot operator does. So, for C dot C it will be C, for C dot P also C, for C dot G also it will be C. For P dot C it will just take whatever the value was, because it is just propagating C, P and G, and for G whatever the second argument is, it does not matter, it will remain as G. Okay. So, essentially the way we define this thing. Okay. So, if a bit is cleared, then it remains cleared. Here if it is I mean if my current thing is P, then I am just propagating what was earlier, and here if it is G, then I mean I am generating the bit. Okay. So, with this we can now define what our Ci will be. Okay. So, now how can I write Ci in terms of these operators? So, Ci is equal to 1 if and only if f of so the previous thing is 1. Okay. If and only if f of I dot f of I minus 1 up to f of 0 is equal to G. Okay. So, you can actually verify this. So, what is this saying? So, this is saying that well at some position Ci plus 1, okay, my carry bit will be 1. If it was generated earlier, okay, if it was generated at some point, okay, that means there exists some j where fj is equal to 1, and thereafter it is either fj is either I mean equal to p or it is equal to g, okay, only then this thing will be equal to g, and if it is getting cleared then of course it will become c again, okay. So, finally, if this quantity is equal to g, then this is equal to 1. Now, how can we construct a gate? So, note that for each fi, okay, so each fi can be implemented using a constant size circuit, okay. Similarly, the dot operator also can be implemented using a constant size circuit because it is taking two arguments, some c and p. Similarly, this can also be implemented using a constant sized circuit, okay. But now we have well I have an expression which has potentially order n dot operators, right. I mean for some Ci I will have I dot operators, I can go as large as n, okay. Now how do I do this, okay, and the question is how do I kind of do this in parallel, okay. So this is where the parallel prefix sum idea comes in. So what we will do is I will use this fact, okay. So I will kind of show that well, and note that these fi's are basically my xi's over here, okay. So what I will show is that I will give the construction of this circuit Pn, which will be a log depth and linear sized circuit, okay, which will essentially compute my fi's. And now once I have my fi's, and I mean it is not just computing the fi's, it will basically be computing f0, then it would compute f0 dot f1, then it would compute f0 dot f1 dot f2, so on till f0 dot f1 dot up to f of n minus 1. And once I have all those numbers, I can just check it with g and I can get the carry bit, okay. So that is the idea. So we know that this is the base case, so we know how to compute P2. Let us see how to compute Pn. So construction of Pn, okay. Let me write this, we will do it recursively from P of n by 2, okay. So we will assume we have a circuit for P of n by 2, okay. That means it takes n by 2 bits and it has the circuit P of n by 2, and then using that we will construct for P of n, okay. So any questions? Okay, so let us see this. Yes, so you can compute any of these parts at any time, and but the respective order should be, see this is not a commutative function. For example, you can see that C dot G is not the same as G dot C. Okay. So, the order must be the same, but which term you want to compute first or last, it does not matter. Yeah. Okay. And that non-commutativity is actually very important over here. Okay. It means that, well, if I have a G followed by anything, it does not matter, the final output would be a G. Okay. So, G dot anything would keep it as G. So, how do we do this? So, let us first assume we have this circuit for P of n by 2. Okay. So, let me just make sure I get this correct. Okay. So, what this circuit will take as inputs are following. So, I will have a gate, I mean I will have a circuit here for the dot operator with inputs x0, x1, this goes over here. Then I will have a circuit for x2, x3, this goes over here as input, and then finally I will have a input which takes x, and assume here that n is even, okay, n is divisible by 2, x n minus 2, x n minus 1. Okay. So, these are the inputs that are going into P of n by 2. So, by recursion, okay, what we get as output are follows. So, here what we will get is that we will of course get first will be of course the input itself. So, we get x0 dot x1. What will be the second output? Write it. Okay. So, this is my x0 dot x1. What is this? So, this is basically this dot this. Okay. So, this will be x0 dot x1 dot x2 dot x3 and so on, and the last one will be x0 dot x1 up to xn. Okay. So, I am just assuming there is a circuit Pn by 2 and this is what it takes as input and output. Okay. Now, I have to give the circuit for n. Okay. So, I have to construct Pn now, which takes this, and I have to now, so note that here there is a jump, right. So, I am not, for example, getting x0, I am not getting x0 dot x1 dot x2 and so on. So, I have to compute those, but note that those are actually easy to compute. How can you get them? For example, how do you get x0? Just output this. How do I get x0 dot x1 dot x2? Exactly, take x0 dot x1 from here and x2 from here. How do I get x0, x1, x2, x3, x4? Again the same thing, take this and then take x4 directly. Okay. So, I will have one, so this directly goes out over here, then this goes out, then for x0 dot x1 dot x2 I will have x2 directly going, this going over here and going out like this. So, this will be x0 dot x1 dot x2, this is x0 dot x1, this is x0, and I basically keep on doing the same thing and finally I get this. Okay. So, now let us analyze what is the size of Pn and what is the depth of Pn. Okay. So, the construction is clear, right. So, if I have Pn by 2, I can get Pn from this. So, what is the size and depth analysis of this circuit? Okay. So, let S of n be the number of dot operators in the circuit Pn, and d of n be the depth of Pn. Okay. So, what is S2? We just saw that S2 is equal to 1, it has only one dot operator, right. And what is D2? Again the depth is 1, so it is 1. Now, what is Sn? What does Sn depend on? It depends on S of n by 2. Okay. So, it is the number of gates in S of n by 2, which is over here, plus I have some more operators over here, right. Here I have how many extra operators? N by 2. Here I have how many operators? Again I have actually used, if you just observe, so this will actually be n by 2 minus 1. Okay. So, I have one less. So, except for this I have again another operator for every two of them. Okay. So, it will roughly be around n minus 1, or even n is okay, it does not matter. And now, if you solve this, what do you get? So, this is like n minus 1 plus n by 2 minus 1 plus n by 4 minus 1 and so on. So, this turns out to be equal to, actually it is bounded by 2n, but I mean we will just, it does not matter, we will keep it as order n is good enough for us. Okay. And then we also observed that each dot operator can be implemented by a constant size circuit. So, therefore, the total size is constant for us, right. What about the depth? Again the depth is similar. So, it is the depth of P of n by 2 plus how much are we adding? So, I have one gate over here and I have one gate over here in the depth. So, plus 2. So, this is, if you solve this, this will be about 2 log n, right. So, this is order log n for us. Okay. So, in addition to the depth here, I have one gate over here and one gate over here, right, in the depth. Okay. So, therefore, addition can be performed by a bounded fan-in circuit of size order n and depth order log n. And this is actually optimal. You cannot, we saw that of course you cannot have a depth lower than log n, and of course you cannot have a size also less than linear, right, because if it is less than linear you cannot even read the entire input. Okay. So, this is kind of the optimal that we can get. Okay. Any questions? Here? Yes. 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 Pn by 4, it will be basically x0, x1, x2, x3 will be the first one. It will be 4 together. Then for the next one, the second input will be 4, 5, 6, 7 and so on. you are going to use these inputs now. So, whatever we have over here, that is being used in Pn by 2, whatever you are getting, I mean,
whatever the inputs of Pn by 2 are, so we are just going to combine.
yes, or Pn by 4. So, it is a recursive procedure. Any other questions?